Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to cover chapter 3 for our physical chemistry playlist, and this chapter discusses the first law of thermodynamics. In this chapter, we're going to cover the following objectives. First, we're going to start with the concepts of heat and work. These are the two main ways that energy can be transferred between a system and its surroundings. So we're going to carefully define both and look at how they're treated in thermodynamics. Next, we're going to move into the first law of thermodynamics itself. This is the principle of energy conservation. Here, we're going to introduce the idea of internal energy and see how it changes when heat or work crosses the system boundary. After that, we're going to introduce enthalpy. This is another state function that is especially useful under constant pressure conditions. We're also going to make an important comparison between changes in internal energy, delta U, and changes in enthalpy, delta H. Then we're going to turn to heat capacity. We're going to look at how it's defined, the difference between constant volume and constant pressure heat capacities, and the molecular interpretation that connects heat capacity to the motions of molecules. We're also going to compare CV and CP and see how they are related. Following that, we're going to study gas expansions. This includes isothermal expansions, where the temperature is held constant, and adiabatic expansions, where no heat is exchanged with the surroundings. We're going to examine how the work expressions differ for these cases. Finally, we're going to end with calorimetry, which is the experimental measurement of heat changes. We're going to look at both constant volume calorimetry, as in a bomb calorimeter, and constant pressure calorimetry, as in a coffee cup calorimeter. All right, let's go ahead and begin with our first objective, heat and work. Thermodynamics, at its core, is the science of heat and temperature and of the laws that govern the conversion of thermal energy into other forms of energy like mechanical, electrical, or chemical energy. Most importantly, thermodynamics is a macroscopic science. This means that we are describing systems in terms of measurable bulk properties like pressure, temperature, and volume, rather than following the motion of individual particles. And by studying these macroscopic variables, we can then predict and quantify how energy is transferred between a system and its surroundings. Now let's focus specifically on work. In mechanics, work is defined as the dot product of force with displacement. So work equals FD cosine theta. Now, if you imagine a piston with a gas inside, the external force from pressure pushes perfectly along the direction that the piston moves. So the angle is 0 and cosine of 0 is 1. That means the dot product reduces to just an ordinary multiplication. Work equals force times displacement. Now, for our piston example, we're going to write that work is equal to force times delta H, where delta H is the displacement of the piston. Next, we're going to connect force to pressure. Pressure is defined as force divided by area. So the external pressure acting on the piston equals the force divided by the piston's cross-sectional area. Rearranging that means the force is now equal to the external pressure multiplied by the area of the piston. Force equals P external times A. We can now substitute this expression for force into our work equation. Work becomes equal to P external times A times delta H. But notice that the piston's displacement, area times height, is directly related to the volume of the gas. The volume of the gas is equal to area times height. Therefore, the change in volume is equal to area times the change in height, and we can go ahead and replace A times delta H with delta V. So substituting this into our work expression, we get that work is equal to P external times delta V. Now we need to bring in the thermodynamic sign convention. By convention here, we consider the point of view of the system. If the system's compressed, then the surroundings are doing work on the system, and that is counted as positive work. If the system expands, the system is doing work on the surroundings, and that is counted as negative work. To account for this sign convention automatically, we're going to add a minus sign into the equation. So the thermodynamic expression for pressure volume work becomes W is equal to negative P external delta V. Let's pause here and reflect on what this means. If the gas expands, the change in volume is positive, and the expression gives us negative work, meaning the system is losing energy to the surroundings. But if the gas contracts, the change in volume is negative, and the expression gives us positive work, meaning the system is gaining energy from the surroundings. That's the step-by-step derivation you've already seen in general chemistry. But now we want to connect this to a more general mathematical form that we're going to use in this course. Up to now, we've treated work with the simple mechanics idea, a force acting through a displacement. In thermodynamics, I want to say that more broadly, work is any quantity of energy that crosses the system boundary because a force acts through a displacement at that boundary. That force displacement pair could be a piston force moving a face of the container. It could be an electrical force moving charge. It could be a surface tension pulling an interface. In each case, energy crosses the boundary because something is pushed along some displacement. Now, in addition, work is also transitory. That means it is not a property that the system has. There is no such thing as the work of the system at a state. Work only appears while a change is happening, during a compression, during an expansion, while current flows, while a surface stretches. When the process stops and the system sits quietly in a fixed state, work is zero and undefined as a property, and we'll see that this is the same case for heat. This is exactly why we track work and heat with path-dependent increments, and we reserve state functions like internal energy, enthalpy, pressure, volume, temperature for describing the system itself. So now to move from the single-step picture to a general one for work, think of carrying out the process in many tiny steps and adding up the tiny contributions. So an infinitesimal amount of work equals the force at the boundary dotted into the infinitesimal displacement of that boundary. So we can write delta W equals F dot dx. For a piston of cross-sectional area A, the external pressure times the area gives the opposing force on the gas. The piston moves a tiny distance dx. Writing that in pressure volume language gives us that an infinitesimal work equals minus the external pressure times the infinitesimal change in volume. The minus sign enforces our sign convention. So we have the following equation. Delta W equals negative P external dV. To get the total work for the whole process, we add these contributions from the initial to the final volume. So in words, the work equals the negative integral of the external pressure with respect to volume taken from the initial to the final volume. Why is this useful? Because it automatically handles any pressure history. If the external pressure is constant, then the integral collapses. You can take P external outside the integral, and what remains is just the volume change. And that's going to return the algebraic form we derived earlier. Work is equal to negative P external d delta V. But if the external pressure changes gradually, as it would in a reversible process, which we'll define shortly, we're going to need this more general form to calculate the work accurately. So this integral form is the foundation we're going to rely on when we move into the next page and discuss reversible and irreversible processes. For irreversible and reversible processes, these two situations look very different mathematically, and they lead to different amounts of work. We're going to start with the irreversible picture. Think of a piston with a single heavy weight on top. That weight fixes one opposing pressure, P external. For example, when the gas pushes in an expansion, its own pressure inside is going to be higher than that fixed outside value. So the piston lurches forward in one noticeable move. The outside pressure, it does not adjust to match the gas. There's a finite pressure difference that's driving the motion. So the system is not in equilibrium while it moves. Because we push against the same opposing pressure for the whole change, the bookkeeping is simple. The work is the negative of that fixed pressure times the volume change. And during an expansion, delta V is greater than 0. It's going to be positive. And the work is negative because the gas, aka the system, delivers energy to the surroundings. The image to keep in mind is a big step on a pressure volume plot. There's a horizontal line at P external, and the rectangular area under that line is the work. Now, any extra driving force the gas had over the external pressure, it isn't carefully harvested at the boundary, so it doesn't show up as additional PDV work. For irreversible compression, a similar logic applies, and we're going to use the same work equation. Now, let's turn to reversible processes. Here, we're going to replace the single heavy weight with a stack of tiny weights that you add or remove one sliver at a time for compression or expansion, respectively. At every instant, the outside pressure is going to be adjusted to be essentially equal to the gas pressure. So in other words, a reversible process is carried out infinitely slowly in such tiny steps that at each moment, the external pressure is essentially equal to the internal pressure of the gas. So the system's always in equilibrium with its surroundings, and this is sometimes described as a quasi-static process. Because the opposing pressure is not fixed, but instead tracks the gas pressure point by point, we can't use one constant value. So the work equals the negative integral of the system pressure with respect to volume along the path from initial to the final volume. Here we are going to keep it simple because the external pressure is essentially equal to the internal pressure at every step. We can rewrite the expression for work as work equals the negative integral of the internal pressure with respect to volume taken from the initial volume to the final volume. If the gas is ideal and the process is at constant temperature, we can substitute the ideal gas law for the internal pressure. That substitution gives that P internal equals nRT divided by V, where N is the number of moles, R is the gas constant, and T is the temperature. Plugging this into the integral gives work equals negative nRT multiplied by the integral of 1 over V dV from the initial volume to the final volume. We took nRT out of the integral because these remain constant. Evaluating this, we get that work equals negative nRT times the natural log of the final volume divided by the initial volume. We can also write this as work equals negative nRT times the natural log of the initial pressure divided by the final pressure because we know P1V1 equals P2V2 from Boyle's law. The picture to keep in mind on a pressure volume diagram for a reversible process is many small, balanced moves rather than one big jump. The reversible path, it traces a smooth curve that follows the gas's own pressure at each step. Over each tiny change in volume, you could draw a thin rectangle whose height is the instantaneous pressure and whose width is dV. And adding all those thin rectangles gives the area under the curve, which is the work. With our pictures for reversible and irreversible processes in mind, let's pull the ideas together. First, the essential difference is how the opposing pressure behaves. So in the reversible case, the opposing pressure is fixed and the system is not in equilibrium while it moves. So the work depends only on that fixed external pressure and the total change in volume. But in the reversible case, the outside pressure is continually adjusted to match the gas at every instant. So the system remains in equilibrium with its surroundings, and the work depends on the entire path. And we determine it by integrating the actual pressure volume curve of that gas. So that path dependence is why the integral form matters. Second, the pressure volume plots make this distinction clear. The irreversible step appears as a horizontal line at the external pressure with a rectangular area underneath. And the reversible process traces a smooth curve that follows the gas's pressure at every small step. The work is then the full area under that curve. Specifically, what we're seeing here is a gas expansion plot for both irreversible and reversible processes. Now, third and finally, for the same starting and ending volumes, the reversible area is larger in magnitude for an expansion. That's seen clearly in the plots. But we don't have plots for compression shown directly here. Maybe I'll overlay it with the video. What you'll notice is that the reversible area for a compression, that's going to be smaller for reversible than an irreversible process. This is why a reversible expansion delivers the maximum possible work, and a reversible compression requires the minimum possible work. Let's practice what we've learned with a couple of examples. In the first problem, we're asked to calculate the work involved in expanding 20 liters of an ideal gas to a final volume of 85 liters against the constant external pressure of 2.5 bar. When the external pressure is constant, the work is given by the expression work equals negative external pressure multiplied by the change in volume. Here, the change in volume is the final volume minus the initial volume. That's 85 liters minus 20 liters. That is equal to 65 liters. Now we substitute this into the equation for work. Work is equal to negative 2.5 bar multiplied by 65 liters. That gets us negative 162.5 bar times liter. If you wanted to convert the units, 1 bar times 1 liter is equal to 100 joules. So multiplying this out would give us negative 16,250 joules or negative 16.25 kilojoules. That negative sign tells us that the gas did work on the surroundings during expansion. Now let's tackle the second problem. This one says a quantity of 0.850 moles of an ideal gas initially at a pressure of 15 atmosphere and 300 Kelvin is allowed to expand isothermally, meaning at constant temperature, until its final pressure is 1 atmosphere. Calculate the work done if the expansion is carried out, A, against a vacuum, B, against the constant external pressure of 1 atmosphere, and C, reversibly. For part A, expansion against a vacuum, the external pressure is 0. So substituting that into our formula for work gives us that work is equal to 0. So in a free expansion, no work is done. For part B, expansion against a constant external pressure of 1 atmosphere, we need to find the initial and final volumes first and foremost, and then we can plug them into work equals negative P external times delta V. Volume is equal to nRT divided by P. So we're going to use that formula to figure out initial and final volumes. For the initial state with a pressure of 15 atmospheres, the initial volume is equal to 0.850 moles times 0.08206 liters times atmosphere per mole times Kelvin, and that is multiplied by 300 Kelvin. All of that is divided by 15 atmospheres. This gives us an initial volume of 1.40 liters. For the final state, with a pressure of 1 atmosphere, the volume is equal to 0.850 moles multiplied by 0.08206 liter times atmosphere per mole times Kelvin multiplied by 300 Kelvin. All of that is divided by our pressure, 1 atmosphere. This is equal to 20.9 liters. That's our final volume. Then the change in volume is simply 20.9 liters minus 1.40 liters, and that is equal to 19.5 liters. Substituting into the equation for work, we get that work is equal to negative 1 atmosphere multiplied by 19.5 liters. That is equal to negative 19.5 liter times atmosphere. If you want to convert to joules, remember that 1 liter times atmosphere equals 101.3 joules. So if we carry out that conversion, we get that work is equal to negative 1.98 times 10 to the 3 joules. So the gas does about negative 2 kilojoules of work in this irreversible expansion. Finally, part C is the reversible isothermal case. In this situation, the work is given by the negative of nR times T multiplied by the natural log of the ratio of the final volume to the initial volume. Because volume and pressure are inversely related for an isothermal ideal gas, we can also write this as the negative of N times R times T multiplied by the natural log of the ratio of initial pressure to final pressure. Substituting the values in, N is 0.850 moles, R is 8.314 joules per mole Kelvin, T is 300 Kelvin, and the ratio of pressures is 15:1. So the expression becomes negative 0.850 times 8.314 times 300 multiplied by the natural log of 15. This evaluates to negative 5.74 times 10 to the 3 joules. So that is our answer for part C. Notice when you compare the values for B and C, the magnitude for the reversible process is greater than for the irreversible process. So the work delivered by the reversible expansion is greater than the work delivered by the irreversible process, and that lines up with what we've discussed. Now, so far, we've focused on work as one way that energy can be transferred between a system and its surroundings. The other major way is through heat. In thermodynamics, heat is defined as the quantity of energy that flows across the boundary between the system and the surroundings because there is a temperature difference. In other words, whenever the system and the surroundings are at different temperatures, energy will flow until thermal equilibrium is reached. And that flow of energy is what we call heat. Heat is also transitory. That means it only appears during a change in the state of the system and surroundings. If nothing changes, there is no stored heat in the system. Heat is not a property of the system, but rather a way that energy is transferred. A very common way of calculating heat transfer is with this relationship. Heat equals Mass times specific heat capacity times the change in temperature. So m is the mass of the substance, lowercase c is the specific heat capacity, and delta T is the temperature change, final minus initial. Just like with work, we have a sign convention for heat. From the system's point of view, if heat flows into the system, we call that positive Q. If heat flows out of the system, we call that negative Q. So positive Q, heat is added to the system. Negative Q, heat is removed from the system. And in conclusion, both work and heat are not state functions. They do not describe the state of the system, but rather the transfer of energy between system and surroundings. Because of this, changes in heat and work are path dependent. That means the exact amount of heat or work transferred depends on how the process is carried out and not just on the initial and final states. With that, we've successfully concluded Objective 1, and we can now move into Objective 2, where we're going to discuss the first law of thermodynamics. This is one of the most fundamental principles in all of science. The law is based on a simple but powerful idea that energy can neither be created nor destroyed. If we consider both the system and its surroundings together, the total amount of energy is conserved. To express this idea mathematically, for internal energy, which is all the energy of a system that's associated with its microscopic components, we can write that the change in total internal energy equals the change in the system's internal energy plus the change in the surroundings' internal energy, and this total change must equal 0. So delta U total equals delta U system plus delta U surroundings. That is equal to 0. From this, we can rearrange to say that the change in the system's internal energy is exactly the negative of the change in the surroundings' internal energy. So if the system loses energy, the surroundings gain exactly the same amount and vice versa. So energy is never lost. It only transfers back and forth across the boundary. Now, how can the energy of a system actually be changed? For a closed system, there are only two possible ways: through heat or through work. So in words, the change in the system's internal energy equals the heat added to the system plus the work done on the system. Delta U equals Q plus W. Finally, we can also express this relationship for infinitesimal changes. This is written as the differential change in internal energy equals an infinitesimal amount of heat plus an infinitesimal amount of work. Notice here that internal energy is a state function, so we write du with an exact differential. But heat and work are path dependent, so we use the inexact differential symbol delta. To elaborate on this, internal energy U is a state function. That means it depends only on the current state of the system, things like temperature, pressure, and volume. If you go from state A to state B, the change in U is always the same no matter what path you took to get there. Because of this, we write its differential as an exact differential. But heat and work are different. Heat and work are not properties of the system. They're only going to exist while energy is being transferred, and the amount transferred depends on the path taken. If you take two different paths between the same initial and final states, the value of heat and work may be very different, even though delta U is the same. This is why we use the symbol delta, which reminds us that Q and W are inexact differentials. So the exact differential belongs to state functions like internal energy, enthalpy, or pressure, while inexact differentials are reserved for path functions like heat and work. And this distinction is important, and we're going to keep coming back to it. In addition, I do want to take just a small moment to offer a microscopic perspective on what's really happening when we say heat or work changes the energy of a system. We use the term internal energy to represent the total energy of all the molecules in the system. But molecules don't just have one kind of energy. They can move from place to place, which we call translational motion. They can rotate about different axes. They can vibrate as the atoms in a molecule stretch and bend relative to one another. And in some cases, electrons can even jump between higher and lower energy electronic states. So together, these different forms of molecular motion and excitation make up the internal energy of the system. Then when we talk about change in internal energy, what we really mean is that the way molecules occupy these different energy states, that has changed. At any given temperature, some molecules are in lower energy states while others are in higher energy states. And this distribution across energy states is what shifts when the system gains or loses energy. Heat and work are simply two ways energy crosses the boundary and alters that distribution. We're going to come back to this idea again when we discuss heat capacity. But for now, let's work through this practice problem together. This problem says a sample of gas in a piston undergoes the following process at 300 Kelvin. 1, the system absorbs 650 joules of heat from its surroundings. And 2, the gas expands from 2 liters to 6.5 liters against a constant external pressure of 2 atmosphere. A wants us to calculate the work done by the gas during expansion in joules. B wants us to use the first law of thermodynamics to determine delta U. And C wants us to state whether the system's internal energy increases or decreases. First, the work. For constant external pressure, the work is given by the equation W equals negative external pressure multiplied by delta V, where delta V is the change in volume. The change in volume is final minus initial, so 6.5 minus 2.0, that equals 4.5 liters. Substituting the numbers gives W is equal to negative 2 atmosphere multiplied by 4.5 liters. That is equal to negative 9 atmosphere times liter. To express this in joules, I'll convert liter atmospheres using our conversion factor. 1 liter atmosphere equals 101.3 joules. That gives us that W is equal to negative 9 times 101.3, which is equal to about negative 9.12 times 10 to the 2 joules. Next, the first law of thermodynamics. In words, the change in internal energy equals the heat added to the system plus the work done on the system. So we write delta U equals Q plus W. Here the heat is absorbed, so Q is equal to plus 650 joules, and we just found out that work, W, is equal to negative 9.12 times 10 to the 2 joules. That is just 912 joules. We can put these together into our equation. Delta U is equal to 650 joules plus negative 912 joules. That is equal to negative 262 joules. So the system's internal energy decreases by about 262 joules. The intuition is that the system gained energy as heat, but it did a larger amount of work during expansion. So on balance, its internal energy went down. To finish off objective 2, we're going to define some important terms that are going to be used constantly throughout this course. So they're very important to understand. When we describe a thermodynamic process, we often want to classify it based on what variable is being held constant or what kind of energy is allowed. 4 of the most common processes are isobaric, isochoric, isothermal, and adiabatic. Let's start with the isobaric process. The word isobaric means constant pressure. In this kind of process, the pressure of the system does not change while the volume increases or decreases. On a pressure volume diagram, this shows up as a horizontal line. The work is equal to negative pressure times the change in volume. And the first law still applies in the usual way. The change in internal energy equals heat plus work. Next, we have isochoric process. The word isochoric means constant volume. If the volume does not change, then the system cannot do pressure volume work because there's no displacement of the piston. So delta V is 0, and that means that work is equal to 0. In this case, any heat that's added to the system directly changes the internal energy. Because work is equal to 0, delta U is now just equal to Q. The third type is isothermal process. The term isothermal means constant temperature. For an ideal gas, if the temperature is constant, the internal energy does not change because internal energy depends on temperature. We've briefly mentioned this in chapter 2, but we haven't seen the relationship that we're going to introduce a little bit later. That relationship will allow you to understand this better. So at constant temperature, delta U equals 0. That means whatever heat enters the system must leave as work, and whatever work is done on the system must leave as heat. So in other words, heat and work are exactly equal in magnitude. Q equals W, delta U is equal to 0. Q and W are equal in magnitude, I want to emphasize, but opposite signs. Finally, we have adiabatic process. Adiabatic means no heat is transferred. The system's insulated from its surroundings, so that heat, Q, equals 0. That means the only way the internal energy can change is through work. If the system does work on the surroundings, its internal energy decreases. If the surroundings do work on the system, its internal energy increases. So we write Q is equal to 0, delta U is equal to W. These 4 cases are especially important because they give us simple rules for relating heat, work, and internal energy under different conditions. And these terms, they're going to come up again and again when we study expansions and calorimetry and in future chapters. So make sure you remember their definitions and their relationships. And with that, we've completed objective 2. We're going to end the video here. In the next part, we're going to start up with the third objective on enthalpy. I hope this helps. Good luck, happy studying, and have a beautiful, beautiful day.